Alright, median of a triangle, definition of median of a triangle. It's on page 240 in your book. It says a median is a segment whose endpoints are a vertex of a triangle and the midpoint of the side opposite the vertex in that triangle. I'm going to put a little shorter definition, or hopefully a little easier one up here, just to tell you what a median is. A median is a segment that runs from a vertex of a triangle to the midpoint of the opposite side. So median, we pick a vertex. Every triangle's got 3 vertices. We pick a vertex, you can pick any of the 3 corners, and you want a segment that goes to the midpoint of the opposite side. So it would look something like that. Each triangle is going to have 3 medians. So that would be another one. That would be another one. And again, we know that each of these is a midpoint. So those 2 have to be congruent. These 2 have to be congruent. And the 2 on the other side there have to be congruent. I'm going to write some things over here on the side. Every time you hear the word median, things you should think of. Anytime you hear median, first thing you should think of, midpoint. So you know if you have a median of a triangle, then there's a midpoint. Well, if you hear the word midpoint, then you know you got to have congruent segments. Congruent segments. Point of concurrency. Point of concurrency, you notice here when we drew in all those medians, if I would have drawn them all straight, they all come together right there at one certain point. That's the point of concurrency, where they all come together, point of concurrency. That point, if you look it up in your book, right there close to median, on page 240, that point is called the centroid. Centroid. So that's the centroid. That's what that point's called, centroid. So another word, every time you hear median, you should think of, or goes along with median, centroid. If you hear centroid, then you should think of midpoints, congruent segments, and medians. Any of those words, they all go together. They're all one group. On this next slide, I'm going to draw in the medians. Again, my drawing probably won't be exact. Find the midpoint over here, connect it to the vertex. Find the midpoint over here, somewhere in that area, connect it to the vertex. That point right there, if mine was perfect, they should all come together at exactly the same point, and that is called the centroid. This is an acute triangle. I know it looks like it's equilateral or equiangular also, but I'm going to call it an acute triangle. And if I call this one an acute triangle, I'm going to call this one a right triangle, and this one an obtuse triangle. And the reason I'm going with those names is because in those 3 categories, we cover every possible kind of triangle there is in the world. Here on this one, if I draw in midpoint somewhere about in there, connect it to the vertex, midpoint somewhere about in here, connect it to this vertex, midpoint somewhere about in here, connect it to this vertex, and we have that point right there. It's called the centroid. The midpoint down here, so you should draw all these in on your paper. Midpoint for this side, midpoint for this side, and they should all cross right there at one certain point, and that's called the centroid. go back, we also have a centroid theorem. And that centroid theorem says the centroid of a triangle is located 2/3 of the distance from vertex to the midpoint of the opposite side of the side opposite the vertex on a median. So it's saying centroid is 2/3 of the distance from the vertex to the opposite side. Now, what that means, if I go back over here, if I tell you that this part from the vertex to the centroid is 2/3 of the total distance of the whole thing through there, then that means there is 1/3 left over for this part up here. And that's what they're saying. The centroid is 2/3 of the distance of the total median. So it's 2/3 of the distance from the vertex of the total median. Well, maybe an easier way to look at that is if I tell you this distance is 10, and that's 2/3 of the whole thing, well then that means this distance down here has to be 5. If I tell you that this distance is 8, then from the centroid to the midpoint over here has to be 4. And hopefully you can see that pattern there, that from the vertex to the centroid is always double or twice whatever it is from the centroid to the midpoint. If I do something down on this other one, say I tell you that this part is 3, and this part up here has to be double that, so it would be 6. And then something a little harder, if I told you that this part was x, from the centroid to the vertex, then it's got to be double that, which would be 2x. Or if I told you this part over here was 4x plus 6, this part has to be half that, which would be 2x plus 3. Now, maybe an easier way to write this theorem, or something easier that you can understand, let's go back here and we'll write it. Change my ink color here. Instead of writing it with the 2/3, we can write vertex, let's put distance. Distance, vertex to centroid is twice, double, the distance, midpoint to centroid. So if we draw in on one of these, if we draw in this, and the centroid's right here somewhere, ends up being right there, that distance is always twice as long as that distance. Now, along with median, over here, let's write the theorem. Gotta remember that theorem, so these are all things that you have to remember when you're dealing with median. And in science class, if you do the centroid, and if you were in here so I could show you, in science class, if you do the centroid, they don't call that point the centroid. They actually call it the center of gravity. Center of gravity. Because every one of these triangles would balance on that point if you had whatever, some kind of stick or whatever to balance it on. All right, an altitude of a triangle. Look up in the book, the definition of an altitude is on page 241. An altitude of a triangle is a segment from vertex to line containing the opposite side and perpendicular to the line containing that side. So with altitude, I'm going to make the definition just a little shorter, hopefully it'll make more sense. An altitude of a triangle runs from a vertex or one of the corners of the triangle to opposite side and is perpendicular to opposite side. So in other words, it's going to go from a vertex and it's going to go to the opposite side, which is this side over here, and we want it to form a right angle with it. So same idea over here, I'm going to write altitude. Some key words for altitude. Perpendicular. As soon as you see perpendicular, you should think of right angles. Knowing right angles should make you think of 90-degree angles. Now again, in the book, right close to where it gives you altitude, if we drew in all the altitudes, I'm going to draw in all the altitudes real quick for this one. If we drew in all the altitudes for this triangle, goes to that opposite side, forms right angles. Now, they all come together at some certain point. That's the point of concurrency again. And for altitudes, the point of concurrency is called the orthocenter. Orthocenter. All right, if on this one, if I go through and I draw the altitude here, it's going to form a right angle down there. Goes from vertex to the opposite side, forms a right angle. Here, vertex opposite side forms a right angle. Vertex to the opposite side forms a right angle. In that point right there, it's called the orthocenter. Quit writing. Orthocenter. Now on this right triangle, if I do it, goes over here, that looks like that's about a right angle. Now if I go from this vertex to the opposite side, well, wherever I draw it in here, it's not going to form a right angle. Where it's going to form a right angle is right along this side. And if I do the same thing from this top vertex, same idea. It's going to form a right angle right down through there. So in a right triangle, if you have a right triangle, the two legs are also altitudes. The two legs are also altitudes. Now, if we go back to this previous one, the medians, if we draw in all the medians for each of these triangles, like you should have done on your paper there, we draw in all those medians, we notice that they all fall inside the triangle. The medians and the centroid are always inside the triangle. For altitudes, and let's put orthocenter over here while we're here. That's another word. As soon as you hear altitude, you should think of orthocenter. For altitudes, the altitudes and the orthocenter aren't always going to fall inside the triangle. Fell inside the triangle in this one for an acute triangle, but for a right triangle, the orthocenter is on the triangle. It's at the right angle. The orthocenter, where they all come together, is right there. Now for an obtuse triangle, if I draw the same triangle here, because I'm trying to make stuff fit in that won't fit. If I draw in all the altitudes, I go from this vertex to the opposite side, forms a right angle. Now if I try to go from this vertex to this opposite side down here, no matter where I draw it in there, inside the triangle, it's never going to form a right angle. So when we were doing distance, we had to do this, and what you have to do is extend this side out, and then you can draw in your altitude. If I go to this vertex, same idea, no matter where I draw it inside here, it's never going to form a right angle with this opposite side over here. So what I need to do is take that opposite side and extend it out, and then I can draw something down here, and it's going to form a right angle down in there somewhere. Now with the orthocenter for an obtuse triangle, well, they never met anywhere. Well, what you have to do then is extend them on out, and hopefully, if I could draw straight, the orthocenter will be there somewhere. So for an obtuse triangle, the orthocenter is outside the triangle. And two of the altitudes are outside the triangle. So if you draw in, if you draw all these in like you were supposed to on this, have something that looks like that, this one's extended out so it comes down here, this one's extended out so it comes down here, and your orthocenter is actually somewhere like in there. That's the orthocenter for that one. Orthocenter for this one's outside there. The orthocenter for this one is going to be right there on the triangle. So the orthocenter and all and the altitudes are inside here, for an acute triangle, on triangle for a right triangle, and outside the triangle for an obtuse triangle. And that's what they're asking you to do down here. It says make a conjecture on the location of the orthocenter for each kind of triangle. For an acute, inside, obtuse, outside, and for a right triangle, on the triangle. It's right at the vertex of the right angle. All right, if we look up perpendicular bisector, in the book, perpendicular bisector is on page 238, and this is probably the toughest one. And it's not really tough, it just gives you the most information. A perpendicular bisector of a side of a triangle is a line, segment, or ray that passes through the midpoint of the side and is perpendicular to that side. Now, the reason perpendicular bisector is a little tougher, it's not just a segment. Perpendicular bisector does those two things to a side of the triangle. And it could be, it doesn't even have to be the side of a triangle, it could be anything. So perpendicular bisector of, let's take this side right here. Perpendicular bisector of that side of that triangle has to be perpendicular to and bisect that side. So it's going to intersect it at its midpoint, and it's going to be some line, if I could draw straight, that comes down through there and forms right angles. So it doesn't have to run from a vertex of the triangle, so you don't have any certain starting point. So let's write in this definition. Perpendicular bisector of a triangle is anything that bisects and is perpendicular to the side of a triangle. So, and you'll probably never see me write perpendicular bisector out. This is how I abbreviate perpendicular bisector. Things you should think of as soon as you hear perpendicular bisector, you should think of perpendicular lines. That means you should think of right angles, 90 degrees. Think of bisector. Since you're bisecting a segment, then you should think of midpoint, congruent segments, the point of concurrency, where all those perpendicular bisectors meet for any triangle, is called the circumcenter. Circumcenter. And that's going to be important for this theorem when we get back to it here in a second. It's called the circumcenter. All right, to draw the perpendicular bisectors for an acute triangle in pick a vertex. And we want to intersect the midpoint. No, don't pick a vertex, I'm sorry. We want to intersect the midpoint of the opposite side, and we want it to be perpendicular. Well, to be a perpendicular bisector and an acute triangle, it works out that it looks exactly like the median and the altitudes that we covered earlier. So we know that these are right angles, and we know that these two segments are congruent to each other. Same thing for each of the sides. Now, in a right triangle, perpendicular bisector, if I find the midpoint here, I want some segment that goes through that point, or some line, it doesn't have to be a segment, goes through that point and is perpendicular to it. Well, the only line that's going to be perpendicular to that is one. Just got to make sure we form a right angle right there. So that's a perpendicular bisector of that side of the triangle. If we find midpoint over here on this side, somewhere about in there maybe, we want to be perpendicular to it. Probably a little off. Want to be perpendicular to it, so it's going to be something that runs, that's terrible, something that runs about like that. It's going to be perpendicular here. And we know that these two parts are equal to each other. We find the midpoint up here. Should probably see what should happen there if I could draw straight. Is that when I draw in this last perpendicular bisector, it goes through there, it forms a right angle, and they should all meet at some certain point, just like these over here all should have met at some certain point. And again, that point's called the circumcenter. Called the circumcenter. For an obtuse triangle, if I find midpoint here, perpendicular bisector, maybe you're going to run something like that, wherever it forms the right angle at. Perpendicular bisector of this side, maybe that's the midpoint, it's going to run something like that, form a right angle. Perpendicular bisector, find the midpoint down here, going to run something like that. And you should see that they don't meet, but if I extend them on up, and if my drawing was worth anything, they should all meet right here, and that's going to be your circumcenter. So again, for an acute triangle, the circumcenter and all the perpendicular bisectors are going to be inside the triangle. For a right triangle, the circumcenter is going to be on the triangle. And for an obtuse triangle, the circumcenter is going to be outside the triangle. But perpendicular bisectors are the ones that sort of look crazy because they're just lines drawn in wherever it can hit that midpoint and form a right angle. So if we go back here, my stuff got erased. Again, perpendicular bisector bisects and is perpendicular to a side of a triangle. Point of concurrency, where they all come together at, is called the circumcenter. If I draw these in, the perpendicular bisectors here for this right triangle, something like that, looks something like that, something like that. That should be a right angle. That should be a right angle. And that circumcenter is right there. draw in these, that's the circumcenter. If I draw in this one, that's the circumcenter. Now the circumcenter theorem, and again, let's go back over here. Perpendicular bisector, as soon as you see that, things you should think of: perpendicular, right angles, 90 degrees, midpoint for bisector, if you're bisecting a segment, midpoint, congruent segments, and now circumcenter also. And we'll go ahead and write this in. The theorem about circumcenter. And the theorem says the circumcenter of a triangle is equidistant from the vertices of the triangle. So circumcenter is the same distance, equidistance, that's what that means, from each vertex of the triangle. So if we go back over here, what they're saying, let me change my color here. This circumcenter right here for this obtuse triangle should be the same distance from that corner of the triangle as it is to that corner of the triangle and as it is to that corner of the triangle. All of those have to be exactly the same. So if I look here on this one, the distance from the circumcenter to that corner has to be the same as the distance from the circumcenter to that corner, and the distance from that from the circumcenter to that corner. Same idea here. Has to be the same distance to that corner as it is to that corner and as it is to that corner. All three of those have to be the same distance. What that tells you here, if it's a right triangle and you have perpendicular bisectors, then that point right there, that circumcenter, is also the midpoint of the hypotenuse of the right triangle. It's got to be the midpoint of the hypotenuse of that right triangle. All right, angle bisectors of a triangle. Just to tell you something here, all of these, the angle bisectors, are always going to fall just like the medians. Medians all fell inside. All the angle bisectors will be inside the triangles. Angle bisector of a triangle, all it is it's anything, a line, array, or segment that bisects an angle of the triangle. So if I'm looking at this angle right here, I just want to bisect it. It's going to split it up into two congruent angles. If I'm looking at this angle right here, I want to bisect it. It's going to go from there to there, and it's going to split it up into two congruent angles. The point of concurrency for the angle bisectors, there should, again, all these should, there should be 3 for every triangle, because each triangle has 3 vertices. Point of concurrency for the angle bisectors is called the end center. End center. So whenever you hear angle bisector, and I'll probably write it out this way just to shorten form, abbreviate, angle bisector, that should tell you that you have congruent angles, because the angle is being bisected. Another word you should think of when you hear angle bisector and triangles is the end center. And this should say end center theorem down here. We'll come back to that theorem here in a second, and we'll write it out. So you should also think of the theorem. Let's go to this next slide. And we will, let's erase all this. We will draw in all the angle bisectors for this. I want to bisect that angle, then I want to split that angle up into 2 congruent angles. So it's going to run something like that maybe. Angle bisector here is going to run something like that. Angle bisector here is going to run something like that. So we know that these 2 angles are congruent. We know that these 2 angles are congruent, so on and so on. And that point right there is called the end center. If I bisect this angle, run something like that, bisect this angle, I could get up here to it, run something like that. If I bisect this angle, that's terrible. Run something like that, wow, that's way off. Now, what should happen right there is those should all come together if I could bisect the angles correctly, and that would be your end center. Bisect this angle, see if I can do a little better job on this one. Maybe something like that. Bisect this angle. Well, look something like that. Bisect this angle. Look something like that. Way crooked. And that is your end center. Hopefully you can draw yours a little better than mine. Terrible drawing. Now, the end center theorem says that the end center of any triangle is equidistant from the sides of the triangle. So, what they're saying there is this end center should be the same distance, and remember when you give a distance, it's got to be the shortest path, so it's going to be the perpendicular to that side. So that distance right there has to be exactly the same as that distance, which has to be exactly the same as that distance. So those 3 distances are always going to be exactly the same. So if this is our end center, the distance from here over to there, forming a right angle, has to be the same as the distance from here down to there, and the same as the distance from here to there. Those 3 distances, the distance at end center is always the same distance from the 3 sides of the triangle. On this one, which is like it's an equilateral triangle, just because that's the way I drew it, it ends up being exactly the same. So this distance is the same as this distance, which is the same as that distance. All 3 of those end up being the same. But it only looks this way for an equilateral triangle. And if you draw in all your pictures like you should, if you draw all these in, you should realize on an equilateral triangle, I could draw any of them. On this first triangle, and this first triangle, and the first triangle on the other two, they all looked exactly the same, because for each of those, the median, the altitude, the perpendicular bisector, and the angle bisector for an equilateral triangle are all the same 3 segments. But for the other triangles, they're a little different. Again, remember that point's called, where they all come together, the point of concurrency. It's called the end center. So the theorem says end center is same distance from all 3 sides of the triangle. The end center is the same distance from all 3 sides of the triangle. Now, a theorem that goes right along with that, I can't remember if they give this theorem in this book or not. Try to find out right now. Right, another theorem that goes along with angle bisector we'll just call this the angle bisector theorem. If a point falls on the angle bisector of an angle, then it is equidistant from the sides of the angle. Now, if I draw a picture up here, if we have some angle, call this angle ABC. And if I tell you that ray, that's terrible, ray BD bisects angle ABC. So that ray is bisecting that angle. Then what that means is the distance, if you pick any point that falls on this ray BD, the distance it is from this side to this side has to be exactly the same. That's a terrible draw. Let's try another one. Let's get this out. Eraser. Let's erase this, erase this, erase this. Why don't you erase? I draw this angle, and we bisect it, we'll call this angle ABC, and we bisect it with ray BD here, so we know that these two angles are congruent. It looks a little better. Then any point that falls on this ray is the same distance from that side, remember distance has to form a right angle, as it is to that side. So any point that we pick all the way out through here has to be the same distance from both those two sides of that angle. It's angle bisector theorem. And again, I'm not sure if this book, yeah, it's theorem 5.4, 5.4, and 5.5. I just found it, I didn't see it before. But any point that falls on that angle bisector is the same distance from one side of the angle as it is to the other side of the angle. All right, another theorem that went along with perpendicular bisector, and this doesn't have to be the perpendicular bisector of a triangle or a side of a triangle or anything. We'll just call this the perpendicular bisector theorem. Sort of goes right along with that angle bisector theorem. If I have some segment, we'll call it QR, and we have some line that comes to it, or a ray or an angle, or not an angle, a ray or a segment or whatever comes to it. And this blue one, we'll call it MN. If we know that segment MN is the perpendicular bisector of segment, or we can call this a line, it doesn't matter, line MN, of segment QR. So if this is, the blue one's the perpendicular bisector of this one, then we know that these two segments are congruent, and we know that that's a right angle. Well, then what this theorem tells us is any point that falls on this perpendicular bisector, so the theorem actually says this, any point on perpendicular bisector of a segment is equidistant from the endpoints of the segment. So what that means, if we pick some point right here and we'll call it point A, point A's got to be the same distance from Q as it is from R. So those two distances have to be exactly the same. So if you're standing on the perpendicular bisector right here, that's you. You've got to be the same distance from Q as you are from R. And that works no matter what point you put on that perpendicular bisector, it's always the same distance from those two endpoints, no matter what point you pick on there. So if I told you something like the distance from A to Q was x plus 5, and the distance from A to R was 3x minus 1, then you know that those two have to be equal to each other. So x plus 5 would have to equal 3x minus 1. So if a point falls on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. So any distance from here to there, here to there, there to there, there to there, always going to be exactly the same. All right, problem 13 says find x and the measure of angle 2. So we're looking for x, measure of angle 2. We're going to find both those here in a second. If ms is an altitude, so this is an altitude, so we know that this right here is a right angle. Altitudes form right angles with the opposite side of triangle MNQ. Measure of angle 1, it's right here, is 3x plus 11, and the measure of angle 2, which is right here, is 7x plus 9. Well, since this is an altitude, again, we know that this has to be a right angle. Well, if that side's a right angle, then angle 1 and angle 2 over here have to together equal right angles, so angle 1 and angle 2 are complementary to each other. So an equation we can set up is 3x plus 11, that's angle 1, plus 7x plus 9 should equal 90, because they should equal a right angle. Like terms, subtract 20 on both sides, end up with 10x equals 70, divide by 10, and you end up with x equals 7. That was part of our answer. Now to find angle 2, we just have to plug back in right here. If x equals 7, then 7 times 7 plus 9, that's 49 plus 9. 49 plus 9 is 58, so angle 2 has to be 58 degrees. Now something else on this problem that didn't really matter, but not only was ms an altitude, but since it came down here and they told us that these two segments were congruent, that meant s had to be a midpoint, and if that's a midpoint, then ms is an altitude, but it's also a median, even though my picture doesn't look like it. It's also a median of that triangle. I think they use that in problem 14 here. Problem 14, picture looks like this. Same picture, MS. Again, my picture doesn't look very good. R comes up here. It's angle 2, angle 1. They tell us that these two are congruent. This is N down here, and Q over here. This time they tell us MS is a median. So MS, right there, is a median. So that means these two segments are congruent. And this is a midpoint. S is a midpoint. Tell us that segment QS, it's right there. I don't know why I don't need the arrow. Segment QS is 3A minus 14. Segment SN is 2a plus 1. And the measure of angle MSQ, that's this whole thing. This time they're telling us that the measure of that is 7a plus 1, so this whole angle, 7a plus 1. Now don't be confused because we don't know that that's an altitude this time. Last problem they told us it was an altitude. This time they didn't tell us that. They want us to find the value of A. And decide whether MS is an altitude. So we got to make that decision. Well, what we're going to do here is, since we know it's a median, we know that these two segments have to be equal to each other. So 3a minus 14 has to equal 2a plus 1. Subtract 2a on both sides. End up with a minus 14 equals 1. Just cancel out. Add 14 to both sides. End up with a equals 15. So that's half of our answer. Now the way we can decide whether that's an altitude or not, they told us what this whole angle right here was. Well, if it's an altitude, that should be a right angle. So we just plug back in here and see. 7 times 15 plus 1 should equal 90 if it's an altitude. 7 times 15. I have a calculator on me so I can come up here and do it. That's 105 plus 1 would be 106. So that means that whole angle right there is 106 degrees. Well, that's not a 90-degree angle, so is MS an altitude? No. So don't assume that it's an altitude just because in the last problem, using the same picture it was, or because it looks like it. This is your assignment, page 243, 15 to 22, 41, 42. Plus there's some bonus problems on 243. You could try them. These here will also count as bonus. You could try them if you wanted. Do all that on a separate sheet of paper if you're doing the bonus.